Hello. In this video we're going to look at the idea of probability a little further. And what we're going to look at is some different things that can happen with events. One thing that can happen with an event when you're finding the probability is you could have an event that has a complement to it. And we'll talk through what that means and how to deal with that in terms of probability. You could also have a couple of events that you want to look at together and the probability of those two events both happening. And so we will look at both of those options in this video. So let's go ahead and go to the notes and get started. Okay, so in this section we're looking at complements and unions of events. We're going to start off with the definition of what complementary events are. Complementary events are two events which together make up the whole sample space. Alrighty. So for instance, one example that I have down here is rain. All right, you can either have rain or you can not have rain. Those two events would make up all the options of weather for that day. It could be either rainy or not rainy. Some other options are you pull up to a light, and that light could either be or you can pull up to an intersection, and that intersection could either have a stop sign or not have a stop sign, or it could have a traffic light or not have a traffic light. So anytime you have that not occurring, that's where you're going to get the complementary events idea. In order to complement or to compute the probability of a complement of an event, what we do is we know that the probability of the event plus the probability of the complement of the event, and for complement I'm just going to put this little slash mark up here, okay, and that's going to be the complement. Together, those make up the whole sample space, and the probability of the whole sample space is a certain probability. Okay? So those should add up to 1. Now that's not typically the way that we write it. There are a couple of other ways that we can write it. We can say the probability of some event E, if I subtract this from both sides, is equal to 1 minus the probability of E complement. Or I could solve that for probability of E complement, and I get 1 minus the probability of E. So those are three formulas that you can, three different forms of the same formula that you can use when you're dealing with complements of events and their probabilities. So let's look at an example. If there is a 1 in 4 chance that it will rain on Thanksgiving, what is the probability that it won't rain? Well, the probability of rain is equal to 1/4. Probability of not rain, using this formula up here, would be 1 minus the probability of rain. So it would be 1 minus 1/4, or 3/4. Notice that's similar to what we looked at in the last section when we were looking at this example. Where was it? Right down here. We were looking at face cards or not face cards. If you pull a card from a deck, it's either going to be a face card or a not face card. So if we want to find the probability of a not face card, that would just be 1 minus the probability of a face card, which would be 1 minus 3/13. So 13/13 minus 3/13 gives us 10/13. Okay, so we've seen it before. We just didn't really talk about it in that way before. So that's how we deal with complements of events. The next thing that we need to talk through are what we mean by two different terms when we're dealing with sets. Because a lot of what we're talking about here is the idea of sets and what they are. Excuse me. So we have two things we can do with sets in addition to looking at complements of them. One is the union of two sets. And if we want to have the union of two sets, it's all elements that are in either of the sets. And the intersection of two sets is all elements that are in both sets. So the key words here are either and both. So if we look at a picture of this, let's say we have some sample space here, and I'm going to just represent that with a box. Okay, I'm going to say that's S for sample space. And we have two events. Let's call them A and B. All right. And if we're looking at the intersection of those two sets, it would all be everything that's in both sets. So it would be everything in here. This would be the intersection. All righty. And if we're looking at the union, it'd be everything that's in either set. So it'd be the stuff over here, the stuff over here, and the stuff in the middle here. Okay, so all of this would be the union. And it would be this because if this was, say, employees at Yavapai and students at Yavapai, all right, I would fit in here because I am taking some classes and I'm an employee of Yavapai. So I fit either one or the other. In fact, I fit both, and that's okay. Now, in order to compute the probability of the union of two events, what we're going to do is we need to look at a little bit of notation. So the intersection, the way we write that is we say it's A and B, and the intersection is this upside down U. Alrighty? And the union, we have A and B. For that, we're going to use a regular U with no stem on it. So that says A union B, and this says A intersect B. So in order to compute the probability of A union B, in order to compute the probability of something being in here somewhere, what we do is we add the probability of A, so we take this probability of something being in circle A, plus the probability of something being in circle B. But notice what we've done is we've double counted these probabilities of things happening in the middle, so I subtract out the probability of something being in the intersection. Alrighty? So that is our probability of the union of two events. Now, if these events have nothing in common, then this becomes a 0. But if they do have something in common, you've got to be careful with that. So let's look at the following example, or the following two examples. The first says, and I just used the words here instead of the symbols because I wanted to make sure that it printed for you. You can do it using some equation editors within Word, but I wanted to make sure you could see what was there. So if the probability of A union B is 0.6, the probability of B is 0.45, and the probability of A intersect B is 0.2, we want to find the probability of A. So what we could do is we could take this formula and plug in what we know. So the probability of A union B, we know that is 0.6. The probability of A, we don't know that. That's our unknown. So I'm just going to put probability of A. Probability of B, we know, is 0.45. And the probability of A intersect B is 0.2. And then we can solve that for probability of A. So notice 0.45 minus 0.2, that would end up giving us a 0.25 plus. And then if we subtract 0.25 from both sides, probability of A is going to be 0.35. Okay? So 0.35 plus 0.45, that would give us 0.8 minus 0.2 gives us 0.6. Now let's look at it if we don't have just all those symbols. Let's say instead, if you draw a card from a 52-card deck, what is the probability that it's either a face card or a red card? So the probability of a face or red. In order to do that, this acts as our A, this acts as our B. We would look at the probability of a face card plus the probability of a red card minus the probability of a red face card. Both of those things occurring. So the probability of a face card, we've done that one before. There are 12 face cards out of the 52 cards. Plus the probability of a red card, well, half the deck is red, so that would be 26 out of 52. Minus the probability of a red face card. And if we look at our red faces, there are 3 diamonds and 3 hearts, so that would be 6 52s. Then we want to go ahead and simplify that, so 12 50-seconds plus 26 50-seconds, that would be 38, minus 6 is going to be 32, so our probability would be 32 50-seconds. All right, and then you can go ahead and simplify that. Okay, but that's the idea of a union of sets. Let's look at the next example here. And for our next example, we want to use this table for the next set of examples. So use the table containing information about income related to hours spent shopping on the internet per month to answer the following questions. So we've got, if folks have an annual income above 60,000, okay, this many spent 10 plus hours shopping online, this many spent between 3 and 9, this many spent between 0 and 2. So there's a total of 496 folks with above 60,000 that they talked to. Okay, there was 512 that fell in this category, and there were 592 that fell in that category. So there was a total of 1,600 folks that they talked to. Then you can also look at these totals as well. So let's look at the following. What is the probability that a consumer we select at random either spends 0 to 2 hours per month shopping on the internet or has an annual income below 40,000? So probability of 0 to 2 or less than 40,000. In order to find that, we'd find the probability of between 0 and 2 plus the probability of less than 40,000 minus the probability 0 and 2 and less than 40,000. All righty? So we're going to go up here and look and say, what is the probability that someone spends between 0 and 2 hours? Well, it would be the number of folks that spent between 0 and 2 hours, which is 544, over the total number of folks that we looked at, which was 1,600. Plus, what's the probability that somebody earns below $40,000? Well, the number of folks that earned below 40,000 was 592, and the total number of folks was 1,600. Minus the probability, notice we took everything in this column, and then we took everything in this row. Well, we double counted this, didn't we? That's the number of folks who had annual income below 40,000 and spent between 0 and 2 hours. So we need to subtract off that 272. Okay? And then that'll give us our answer, which comes out to be 864 1600ths. And we can simplify that, or we can turn that into a decimal. Okay? All right, the next question. Using the same table, what is the probability that a consumer that we select at random either spends 10 or more hours per month shopping on the internet or has annual income between $40,000 and $60,000? So, same thing. Probability of 10 plus or 40K to 60K. We're going to look at the probability of 10 plus the probability of 40 to 60 minus the probability of 10 plus and 40 to 60. Okay, so if we look at our numbers here, the probability of somebody having 10 plus hours, well, we've got 480 folks there out of the 1,600 total, plus the number of folks between 40 and 60 is 512, minus the probability of folks that do both would be these folks, 160. over 1,600. And that comes out to be 832 1600ths, which if we turn it into a decimal is 0.52. All right, last one. This is a little bit of a twist on it. What is the probability that a consumer we select randomly neither spends more than 2 hours per month shopping on the internet, nor has an annual income of $60,000 or less? All right. How would we go about doing that? Well, they neither, so they don't spend more than 2 hours per month shopping on the internet, and they don't have an annual income of $60,000 or less. All right, so where is that going to be? Well, what we could do is we could say, I'm dealing with probability of let's look at 0 to 2 and above 60,000. And the reason I'm looking at that is because it says they don't do those things. So if I could find these, that's a lot of folks. So if I could find those that are between 0 and 2 hours and those that are above 60,000, alrighty, that's going to be the ones that are neither of these other two things. So it's going to be just these folks right here. So it'd be 128 over 1,600. Okay, those folks didn't spend more than 2 hours. They spent less than 2 hours. Whoops, can't see that. So those folks didn't spend more than 2 hours. They spent less than 4 hours. And they didn't have an annual income of 60,000 or less. They were above 60,000. All right. So hopefully that's not too confusing with the wording. So there's some ideas to how to deal with multiple events that we're interested in.